Hello, my name is Nathan Luzum, and I'm a second-year medical student at the Medical College of Wisconsin. Over the past year, I have worked on a project in the Department of Biomedical Engineering that is focused on the fabrication of a biomaterial with distinct layers of polymer nanofiber alignment intended for use in a prosthetic heart valve. The motivation for this project stems from the shortcomings of current prosthetic heart valve biomaterials. Mechanical valves, or valves created from synthetic materials, show excellent durability but require lifelong anticoagulation, which can be very difficult for patients. On the other hand, bioprosthetic valves, or valves composed of treated animal tissue, do not require anticoagulation but will require reoperation within 20 years, making these an undesirable option for younger valve replacement candidates. Therefore, there is a need to develop prosthetic heart valves from a biomaterial that combines the hemocompatibility of treated animal tissue and the durability of synthetic materials. The proposed strategy to address this need is the development of a biomaterial with unique mechanical and magnetic properties. By incorporating magnetic nanoparticles into the material, we believe that magnetically tagged endothelial cells will be captured and retained, limiting the need for anticoagulation. Through the alignment of polymer nanofibers, it is thought that a valve with similar durability to current mechanical valves can be created. Our hypothesis is that modifications to the standard electrospinning process can be used to create a tubular, magnetized biomaterial with distinct layers of longitudinal and circumferential alignment. This material will have anisotropic mechanical properties and the ability to magnetically capture and retain endothelial cells. This project has three distinct aims, which are to achieve unidirectional alignment of electrospun nanofibers on a flat collector, to achieve circumferential alignment of electrospun nanofibers on a drum collector, and to conduct in vitro characterization of the biomaterial. Electrospinning, which is a fiber fabrication method that applies a voltage to an extruded jet of material solution, was used to create this biomaterial. I first electrospun a flat sheet of polyurethane using two separated grounded collectors. The gap between these collectors creates a uniform electric field that guides fiber alignment. This step was repeated with polyurethane mixed with magnetic nanoparticles. Once this bilayer material was generated, it was wrapped around a drum collector with the direction of alignment parallel to the long axis of the drum. Next, polyurethane was electrospun using this drum collector while rotating at 1000 RPMs, allowing for the mechanical forces of rotation to drive fiber alignment in the circumferential direction. The final intended multi-layer valve product is shown in the top right figure, with an inner magnetic layer, a second layer that is aligned longitudinally, a third layer circumferentially aligned polyurethane, and finally a fourth layer that contains magnetic nanoparticles. This composition ensures that both blood contacting surfaces of the valve leaflet are magnetized, while the inner layers provide mechanical anisotropy similar to native valve tissue. Next, a metal valve frame is added with masks that prevent adhesion of the final layer of polyurethane with the valve leaflets, allowing for proper valve dynamics. Scanning electron microscopy was used to analyze the fiber alignment of each layer individually, and images were analyzed with the NIH ImageJ program that utilizes a Fourier transform method to quantify directionality. A 3-axis magnetometer was also used to quantify the surface magnetic field strength of the magnetic material. Image analysis revealed that gap electrospinning method was very effective in aligning the polyurethane fibers, with over 70% landing within plus or minus 10 degrees of the primary axis of alignment. Unfortunately, using the same method with the addition of magnetic nanoparticles resulted in completely random alignment, suggesting that the layers of aligned and magnetic materials must be distinct, limiting the maximum magnetic field strength that can be obtained. Drum electrospinning was not as effective as gap electrospinning in obtaining fiber alignment, but still resulted in 37.3% of fibers within plus or minus 10 degrees of the primary axis of alignment. Although not shown on this poster, this method was also unsuccessful in aligning fibers containing magnetic nanoparticles. Finally, surface magnetic measurement suggests that appropriate magnetic fields can be attained using this protocol. Overall, these preliminary results support the feasibility of producing the desired biomaterial. Mechanical testing, endothelial cell capture and retention studies, and other in vitro tests will be used to further evaluate this material with a long-term goal of testing this valve material in an animal study.